You should have your Chromebooks if you want to check your work that we had the other day. You want to talk about any of that, any of the stuff that you were having trouble with. Yeah. Yeah, there's only 2 right now. She'll be back at some point, but she hasn't dropped or anything. She's just absent. I haven't seen her in a while. Yeah, she's just absent. So. Okay. All right. So we had intermolecular forces here. Remember, intermolecular are between molecules, and intra are between atoms, so within that molecule. Intermolecular forces, examples of those are dispersion, dipole-dipole, hydrogen, ion dipole, and then intramolecular forces would be like covalent and ionic. If we were trying to figure out the types of bonds here, if they're ionic, polar covalent, or non-polar covalent, we look at the electronegativity differences. If the electronegativity difference is higher than 1.67, then it's going to be an ionic character. If it's between 0.4 and 1.67, then it's polar covalent. And if it's less than 0.4, then it's non-polar covalent. So if we look at these between the hydrogen and phosphorus, the difference between those is 0. So that's covalent, non-polar covalent. Between carbon and hydrogen, it's 0.4. So that's non-polar covalent, right on the edge of polar covalent. Magnesium and chlorine is a 1.8 difference. So that's ionic. Lithium and bromine is the same. Phosphorus and oxygen, the difference is 1.4. So that's polar covalent. And nitrogen would be 0, and that's non-polar covalent. We talked about 4 types of intermolecular forces and the types of intermolecular forces that would be seen. So the first one is dispersion force. And when we look at dispersion force, if we look at this, I gave an example of CH4 here. I'm going to make this bigger so I can kind of draw in here. If we look at this, our carbon, okay, why are you not letting me draw? Oh, because it's, okay. It's not going to let me draw because it's not letting me draw in Adobe anymore. All right, so I gave an example there of methane. So methane looks like this. And while these bonds might end up being right on the edge of being a polar bond, because the distribution of charge is distributed evenly throughout this entire thing, this ends up being a non-polar molecule. So you can have polar bonds between atoms, but end up with a nonpolar molecule. And if we have a nonpolar molecule, that is always going to be just London dispersion forces. That's all that's going to be present there. Okay? Remember, those London dispersion forces are the ones that kind of slosh back and forth. So if we're filling out this section down here early, we can go ahead and put LDF down here. Okay, the next one on my answer key that I gave was HCl. So that's the dipole-dipole here. So you've got your hydrogen and you've got your chlorine here. And if we look at the electronegativity differences, we can see that this is going to be a polar bond. And what happens is this chlorine kind of becomes an electron hog. Because it has such a high electronegativity, the electron from the hydrogen is going to end up spending more of its time on this side than it is on this side. So that's going to give this side a positive charge and this side a negative charge. That's a permanent dipole. So that means that we are going to end up having London dispersion forces, and we will also have a dipole-dipole here. Okay, and when we look at that, we can check to see if it's going to have hydrogen bonding. So yeah, it has hydrogen, but it doesn't have that fluorine, oxygen, or nitrogen. So there's no hydrogen bonds here or bonding here. So because of that, dipole-dipole is the strongest force this one will end up having. Then if we look at the hydrogen bonds, kind of the quintessential example of that is going to be water. So hydrogen bonding, you're going to have water. You have your oxygen molecule here. Remember, it has a very, very high electronegativity. It's one of the highest on the periodic table. And because of that, it's going to draw the electrons from these hydrogens up towards this oxygen. So that gives this end of the water molecule a positive charge and this end of the water molecule a negative charge. And when we check for hydrogen bonding, remember it has to have hydrogen. That hydrogen has to be bonded to an oxygen, fluorine, or nitrogen. And that oxygen, fluorine, or nitrogen has to have at least one lone pair. So this definitely has hydrogen bonding as part of it. Okay? If we skip down here and look at this, when we draw our NH3 here, we've got our nitrogen, we've got our hydrogens. We know everything has LDF. We can tell because of this right here, the lone pair of electrons, that it's going to have dipole-dipole because it's going to be a polar molecule. If it has a lone pair of electrons on the central atom, we know automatically that it's going to be dipole-dipole. Then we have to go and we have to check for hydrogen bonding. Is there a hydrogen bonded to fluorine, oxygen, or nitrogen? If it's yes, then we keep going. Does that nitrogen, fluorine, or oxygen have a lone pair of electrons? Yes, so that means that this has hydrogen bonding. Fluorine and fluorine, when they're bonded together, everything's equal here. We have 0 electronegativity difference, so the only thing that's present here is LDF. And the same thing for the same reason for F here as well. Here we have our sulfur. We have our hydrogens coming off of that. We have lone pairs of electrons here, so we know that there's going to be a negative charge on this end and a positive charge on this end. So this definitely has dipole-dipole. Now we check for hydrogen bonding. This is not fluorine, oxygen, or nitrogen, so there's no hydrogen bonding here. So dipole-dipole is the strongest force that we have here. The next one is carbon dioxide. We have carbon dioxide. We have this molecule ends up being completely balanced here. And so because of that, all that's present is LDF. And then chlorine is the same as the hydrogen and the fluorine. All that's present is LDF here. Any questions on number 4? Anything not make sense there? All right. How does the strength of the intermolecular forces affect the boiling point? If you have an increase in IMFs, that's going to equal an increase in boiling point, because it's going to hold those molecules together tighter and prevent it from changing into a other substance. Altitude affects boiling point. As we increase our altitude, increase in altitude is a decrease in pressure, pushing down the atmospheric pressure. And so there's less stuff pushing down on it, so that leads to a reduced boiling point. So water will actually boil at a lower temperature in Denver than it does here. State the thing that's happening here. Melting, we are going from a solid to a liquid. Evaporation, we're going from a liquid to a gas. Sublimation, we are going from a solid to a gas. Condensation, we're going from a gas to a liquid. Boiling is a liquid to a gas. Deposition is a gas to a solid. Freezing is a liquid to a solid. And vaporization is where we go from a liquid to a gas. Evaporation and boiling are both forms of vaporization. All right, intermolecular forces are attractions between two or more molecules of atoms. Okay, IMF is based upon the polarity and Coulomb's law. We talked about Coulomb's law in terms of how close things are. The closer two things are together, the stronger the force between them. For intermolecular forces, from weakest to strongest, you've got your LDF. You have your dipole-dipole. You have your hydrogen bonding. And you have your ion dipole. The stronger the IMF, the greater the interaction between the two particles. This is going to result in a higher melting point and boiling point, since it requires more energy in the form of heat or compression to disrupt the intermolecular forces between them and permit a phase change. Blended dispersion forces then are present between all substances, polar and nonpolar, both. The only IMF that nonpolar particles exhibit are LDF. As two particles get closer together, the LDF interactions increase in strength. That's because as you decrease the distance between the two particles, the Coulombic repulsion of the two particles in the electron cloud will force the electron density to redistribute, introducing a temporary or instantaneous dipole. But again, it's instantaneous. It comes, it goes. As you increase the molecular size, you increase the strength of the LDF. I guess I should say that increases. That's what should go in the blank. The strength of the LDF increases. And it's not dealing with the molecular weight. Remember, I talked to you guys about this. The key was not molecular weight. The key was actually what? And molecular weight is an indication of this, but it's actually the what? Number of electrons. Because we've increased the number of electrons here, which the molecular weight kind of gives us a clue to that. Because we've increased that, we have more electrons that we're able to distribute between here. And so that's why the LDF increases. Okay, it has to do with that electron cloud. All right, nonpolar substances do not have a dipole moment. When a polar particle approaches a nonpolar particle, the polar substance induces a temporary dipole that wasn't there originally. This temporary dipole occurs in order to maximize Coulombic attraction and minimize the repulsion. To recall that polar substances have dipole moments. Dipole forces are present between two polar substances. Okay, so the negative dipole of one polar molecule is attracted to the positive, and the positive dipole is attracted to a negative. When we're dealing with hydrogen bonding, the polar substance has a hydrogen that is bonded to a highly electronegative atom. The hydrogen bonding is extremely strong, so strong that it can stably maintain a structure of large macromolecules such as proteins or nucleic acids. Ions are charged. They have a permanent dipole. Ionic bonds occur between a cation and an anion due to the transfer of electrons. Ionic bonds are present between metals and nonmetals in solution, and ionic bonding is the strongest IMF. All right, any questions on that homework sheet? All right. So I want to turn our attention over to solids and liquids here. I don't know if this will let me write on here or not. All right, so when we have solids and liquids, you got, I think, a Venn diagram there on your notes, in your note packet. Okay, they are both matter. They both take up volume. They all have particles. Okay, so if we're looking at similarities between them in our Venn diagram, we can see those things occurring. Okay. It's a continuation of notes that we had started for IMFs. All right, intermolecular forces, then, if we're looking at solids, they are highly ordered. They're locked into a specific matrix. There are two types.
The 12.3 solid liquid notes.
Yeah, do you see a Venn diagram that looks like this?
I'm trying to make sure it was the right one.
Okay. And then your liquids are disordered, but the particles can move around. They take the shape of their container, and they have various properties. So I'll let you write those down. Give you a minute to get that Venn diagram set up and kind of think about it for a minute. I think it seems pretty logical.
Have to be all yours if you want to change your schedule.
No, not feeling it. You good?
Oh,
Almost.
not yet, sorry. I need to take a picture of it.
No, it's fine, honey. Don't worry about it. Take your time.
You can switch if you want to, no, I'm good.
Okay. So we have what's called a cooling curve or a heating curve. So if the curves tell us how we're going to transition from one form to another. So if we're going to go from a solid to a liquid, we would have a heating curve. And we were going to go from a liquid to a solid, we would end up with a cooling curve, which makes sense, right? You're going to cool it down. And that's going to show us how we transition. Good?
Yeah, I'm good.
All right. So water is in a solid phase. It's going to be locked in position. As a liquid phase, it can move. And as it is cooled, it can turn into a solid. And if allowed to continue to cool, then all molecular motion stops when we get to absolute zero. So solids have a specific matrix that they're locked into. Okay? We have something called an amorphous solid where that's not a repeating pattern. Okay? And it's put together in kind of all different shapes. And you can see like the shape here versus the shape here versus the shape here. It's just kind of a hodgepodge. All right? And if you think about the substances where this happens, with the exception of glass, these are all things that are kind of squishy or moldable or movable or pliable, right? And that's a result of this kind of random pattern here. Okay. Glass is an example of this, and you don't think of it necessarily as flowing, but if you look at like old buildings where there's glass that's in there that's been in there for a long time, you'll sometimes see that it's starting to kind of pool down here at the bottom, and it distorts the image when you're trying to look through it. So if you've ever looked through, like been to a really old building that's had really old glass in it, you'll notice this. You also see this sometimes in glass where it's been kind of like cheaply produced. And that is a direct result from this kind of mishmash of shapes here. Okay. We also have a crystalline pattern. Okay, so this was all already written on there. That's why I kind of made it smaller. And then this is the bigger one. But you can see the difference between these two images. This is your amorphous. This is your crystalline. See that mishmash here, random versus a very defined repeating pattern. Good?
Yep.
Okay, so liquids show what's called translation. The molecules in the liquids are able to move past one another, and because of that, they can take the shape of their container. this is kind of interesting. This guy started one of the properties of liquids is viscosity. Viscosity is a resistance to flow, and high viscosity means that it's going to flow slowly. So don't write any of this stuff down here or this chart or anything. Just write these like couple lines right here. Okay. I'm going to talk about this when you're done writing. Good?
Yeah.
Okay. So what this guy did, and I think he's gone now. I think he's probably passed away, but back in 1927, he poured this hot pitch. This is what they use like to, sometimes you'll see like asphalt pavement and they've got this line of stuff running between cracks to kind of seal it up. That's what that pitch is. So, and like during the summer, it gets hot and you feel like put your shoe in it or something and kind of feel like it's kind of sticky a little bit. He poured this pitch in here and he waited 3 years and then he cut the bottom of this funnel out. And 8 years later, the first drop finally fell. Okay. Fast forward here to 2014. We've had 9 drops fall. Now, why did it slow down so much in between these years? My guess is that where they were at, they probably got air conditioning in that university. You know, so because of that, things are starting to slow down a little bit here. It's taken like 14 years between drops here as opposed to like 10 back in here. So my guess is that they probably air conditioned the place and that's what slowed it down. But so far, I mean, it's been running for, this experiment's running for a long time. All right, so high viscosity, something with a high viscosity, it's going to flow slowly, would be like this pitch. Honey would be a good example. You try to like pour honey out of something and you see how slow that flows out of there. Or molasses. I don't know if you guys have ever eaten molasses before. That's kind of a common thing down south, but up here it's not quite as common. And then something with low viscosity would be like water or alcohol. Now, if it has a high viscosity, that means that it has high intermolecular forces compared to these other things. Okay, so this viscosity is a indicator of the IMFs present. So if you were to look at the IMFs between water and this pitch, the water would have low IMFs compared to the pitch. That makes sense? All right. All right. Surface tension is another example of a property of liquids, and it's based on intermolecular forces. Something with a high surface tension is going to have high intermolecular forces. And water has a high surface tension. You can see like a bug. Have you ever seen bugs like walk on water before? You can like float a paper clip on water. You can get water to kind of go all the way to the very top, even over a little bit the rim of a glass. So those are examples of surface tension. The molecules are attracted to one another, and they're going to act kind of as a layer of attraction on the surface of that liquid. High surface tension means high intermolecular forces. Good? No?
Yeah, you're good.
Okay. We can modify this surface tension with something called a surfactant. And that's going to reduce the intermolecular forces. It's going to reduce that surface tension. And something like a detergent is an example of that.
Is that one of our sheets?
Surfactants?
Yeah.
I don't know.
Yeah.
It modifies surface tension. I mean, it's part of the surface tension one section
Oh, okay.
because it's going to change the surface tension. Like
Okay.
it modifies it. It reduces it. This is kind of a practical application of this. So for example, sometimes during the summer, you'll get little fruit flies in your house, and you can take like a bowl with apple cider vinegar, which will attract those fruit flies, and you can set it out. And if you put 1 drop of like Dawn dishwashing liquid or whatever you wash your dishes with, if you put that in there, it's going to change the surface tension of that apple cider vinegar. So when that fruit fly lands on that apple cider vinegar to feed, it'll start feeding there, but because it doesn't have the normal surface tension that it's used to, it'll go right to the bottom and drown. And so that's one way you can get rid of fruit flies in your kitchen during the summer. All right. So mixing of liquids is the next thing. Here we go. Give me just a second here. I gotta switch this recording up here. Hold on a second. I gotta make this bigger. I got to stop presenting here, and then I have to switch, and I have to go to present now, and I have to present a tab now. And find the tab that I want. Yeah, here it is. Okay. Otherwise, at home, they won't be able to hear the video. So. All right, let's try
Molecules of water. First, take an empty pop bottle and fill it with exactly 1 cup of water. Add another cup of water.
Hi, Mom.
Mark the 2-cup level with a marker. Now dump out the water.
Why do I have to do all the work around here? There you go. You're welcome.
Now, add a cup of water to the bottle.
Notice when she's doing this that she's scraping this off, and that's because of the high surface tension of the water here. It's able to come up over a cup when she fills that. So she's scraping that off so that, see?
Now drop in some food coloring so you can see it better. Get your parents to have you add 1 cup of 99% rubbing alcohol. The kind you get at the pharmacy.
See, 1 plus 1 doesn't always equal 2. There are a lot of spaces between the alcohol molecules, little pockets where the water molecules can fit. So when you mix the cup of water molecules with the cup of alcohol molecules, you don't get 2 cups of liquid.
It's a molecule thing. You can learn a lot about molecules just by mixing.
So that's, I think it's a great kind of example of that mixing. Present now. Yep, I want to present my entire screen now again and go here. If the other thing is if you are taking AP Chem, we will come back to that demonstration several times in AP Chem. Or if you get into college, that sort of thing. When you mix those two liquids together, in addition to that reduction in volume, there's also, oh yeah, we will come back to this too in here as far as the reduction of volume, because when we get into solutions later this year, when we're making our own solutions, that comes back into play. But the other thing that if we did this in class, and normally I do, but I don't have enough to go around like for 10 sections. I just have enough for 5. So that's why I just show the video this year. But the material in there heats up too. It's an exothermic reaction. So that's kind of an interesting part of that as well. So, all right. So heating curves and cooling curves is where we will pick up on Friday. So make sure that you tune into that video on Friday. Okay.
Oh, that's right. There is school on Friday. She's like, we're okay.